Today's presenters are Herb Schoeneman and Paul Congaldi. You may remember Herb from the last webinar on product mechanical shock and fragility testing. Paul is a Director of Engineering Services here at Westpak and has been with us for 17 years. He also serves on the ISTA Testing Council. Paul, take it away.
Thank you, Greg, and good afternoon, everybody. Hope everyone's having a great day. To get started, hold on. Let's look at the agenda of what we'll be reviewing today in our webinar. We're going to look at package integrity testing. What are the functions of a package? Review of common test specs and standards. The distribution environment. Package design versus distribution environment. Critical elements or specific test inputs within a package integrity test. Package integrity versus package performance testing. Interpretation of the results and benefits of the package integrity testing.
Hi, this is Herb, and I wanted to make it look like we got a full plate with this kind of an agenda, and indeed we do. Be aware that we're not going to go very far in depth with a lot of these things. Certainly in terms of the package function we will, but we're going to be treating all of the other things very much in depth in upcoming webinars. We've gotten feedback that says, hey, we want to know more about interpretation results or package design, or how in the world do you measure distribution environment. And so we're going to go into those deeply and in depth and all that kind of stuff at upcoming webinars. So if you have a specific want or investigative area, chances are pretty good we'll be covering it, but not, probably not in this one. We're going to go over the top of a lot of these things, mention them, but we will in fact go into in depth in all of them in the future. Paul, take it away.
Okay, thanks, Herb. So before we get into the details of a package integrity test, let's take a step back and look at the history and where it all started and where it came from. During the early years of single parcel shipment, the default shipping test was almost always to ship the product via UPS through the Chicago hub. For whatever reason, this facility had the reputation of being able to true up quickly and dispose of almost any package that wasn't rugged. So it was a good worst-case scenario. Another favorite ship test alternative was shipping via parcel post through the central New York area and back again. Lots of other scenarios existed as well. By the late 1960s, considerable effort was directed towards defining exactly what the shipping environment consisted of, how it might be quantified, and most of all, how it might be brought into the laboratory in a controlled and reproducible manner. The simple fact is that a shipping test is the best possible hiding place for significant product, packaging, or distribution-related problems, regardless of the product, the packaging, the shipping environment, or almost anything else. Beginning in the 50s, considerable effort was expanded towards a unified quantification of the distribution environment hazards. Numerous studies, many from military sources, attempted to quantify inputs such as vibration, impact, temperature and humidity extremes, altitude, negative pressures, top load compression, and similar. Resulting from this effort was a series of papers and articles that, when taken in total, offered a pretty good quantification of the distribution environment hazards. Specifically, impact levels were quantified in terms of drop height as a function of package weight, orientation of impacts, and total number of impacts. Vibration levels in vehicles were quantified in terms of their input spectra, duration, and overall intensity. Temperature and humidity extremes were quantified in terms of their duration and intensity, and altitude levels and top load compression were similarly quantified. When put together in a coherent format, these quantified hazard levels will uniquely define the input levels for both mean and extreme values, as well as the sequence of the likely hazard inputs. When this data is correlated to a package system of the similar size and mass as the anticipated one, then a reasonably good statistical probability exists that a lab test using these inputs will indeed duplicate the hazards of the intended distribution environment.
When I hear that the kind of background, I get a little more wrinkled because I lived through a lot of it. My first job out of school was working for the Western Electric Company, part of the Bell system at that time, in the western Chicago area. And that was the very early 70s. And guess Chicago typically through the was also considered a wild and hazardous place for pack. Got the opportunity to visit this UPS facility in Chicago several occasions, and it was a warehouse 7 to 9 stories tall, and it had a number of holes in the ceilings and roofs of the various floors where these conveyors would go back and forth, up and down, in that particular case, carrying an amazing variety of stuff, mostly packages. And I went through there twice, and on both occasions had opportunities to see packages that kind of got scraped or didn't quite make it through the hole in the ceiling or floor, and they dropped the entire length of that particular floor or ceiling. So it was intense. It was a pretty crazy place. Now, I don't want to imply that that's the case today. Both Federal Express and UPS do a marvelous job with state-of-the-art equipment nowadays, but I can see why that reputation came about. In addition, Paul mentioned a lot of this distribution environment quantification, I'll call it, came about through military efforts. A lot of that kind of stuff was brought together in a document that we refer to as FPL-22. It was a Forest Products Laboratory report number 22, published in 1979. And what it did was it summarized a lot of different papers and studies of the distribution environment, many of which were, in fact, military. And a lot of them dated back to the 1950s and 60s. But that was our Bible for quite a while, for at least 10 years. And we're going to be talking more about that. But that was exactly how we did it. That's how we quantified the distribution environment. And we're going to be talking about some of the equipment they did it. But it's interesting when you go back in history and you've actually lived through it. You can say, "Yep, I've seen that thing. Holy cow!" So anyway, enough for the background. Paul, can you take us forward here?
Absolutely. So since we are talking about packaging and package testing, let's discuss exactly what a package does. We're going to look at the 4 main functions of a package system. There are others, but the 4 ones we're going to focus are containment, protection, communication, and convenience. So one of these functions is containment, which is essentially to contain the product, pretty self-explanatory. It isn't necessarily to protect the product, but rather contain it in a manner that's consistent with the need of the product. This could be a box containing products that aren't necessarily fragile. Examples of this is like shipping pots and pans, action figures, toys, and so forth. Protection. Another function of a package is the protection. Here's where a package will actually help a product that's fragile. If you're shipping a sensitive product, say a server, computer, medical instrument, and similar, the package will need to protect its content from environmental hazards such as shock, vibration, temperature, and humidity. In some cases, say when shipping hazardous materials, the package functions in protecting the environment from the product, so the other way around. If you're shipping, say, 90% concentrated sulfuric acid, the package will need to have enough absorbent material to contain the liquid if there was a spill. This is actually required by law in the DOT. Same for other chemicals that are marine pollutants and so forth. Another important function of a package is communication. A great example of this is a nutrition label on food that communicates total calories, fat content, the carbs, the vitamins, protein, fiber, and so forth. It can also be communication in regard to the functions of the product, for example, product assembly or operating instructions. Or it could be marketing, which is pretty important. Does it have eye-catching graphics, phrases that say new and improved, and other items that will help sell it and from the product next to it. And finally, convenience is the 4th function we're going to talk about. Convenience would be to access the product by using the package itself. For example, a cereal box is not only used to ship or store product, but it also serves in the manner of dispensing it. Another great example of this are the packages that hold disinfectant wipes, where it's used to access the product and allow it to seal back up, keeping them fresh. Now, a package doesn't necessarily have to utilize only one of these functions. All 4 functions can be wrapped around in one box. No pun intended.
Pardon me while I chuckle on the pun. Good point, and the point that Paul made, which is really important, is depending on the product, the function that could change. So, or so-called class. I mean, these were taught to me in the 60s at Michigan State. Maybe still taught that way. I'm not sure, but surely there are other functions. But it all depends on what the product needs. So we're not trying to say these are the only functions. These are just the ones we're going to concentrate on in our testing function of the package. So when we test a package, we actually test it against these functions, and that's really why I was into the discussion. Paul, back to you.
Okay, so a lot of what we test here at Westpak is considered protective packaging, or the protection function that we just discussed on the previous slide. What we're often concerned with is whether or not the product can get to its end user functional and free of any damage, whether it is functional damage or aesthetic or cosmetic. Now, we do offer other tests as well, such as scuff resistance and other tests that test the communications functions, let's say label, for example, but for this webinar, we're going to just concentrate on the protection. One of the functions of a protective package is to mitigate shock into the product, which can occur during drops, kicks, and objects impacting it. Shock can also occur during the sorting line and distribution hubs, where diverters programmed to shift packages weighing over 70 pounds make contact with your 5-pound package. You can imagine the force of the impact. The cushion system should be optimally designed to attenuate the deceleration levels to a level less than the fragility of the product. Another aspect of a protective package is to attenuate vibration resulting from transportation. Unlike shock, which is a matter of probability, vibration is guaranteed to occur 100% of the time when you ship a package. The cushion system should again function to attenuate the vibration input at the resonance of the product. The resonance is the frequency at which the response of the product is highest compared to the input, and is typically where damage occurs. A poorly designed package can actually amplify the resonance of a product, which can in turn destroy it. Shock and vibration aren't the only elements to protect against. A package can be designed to thermally insulate a product. Certain products, such as live tissue or pharmaceuticals, even food, must be kept within a certain temperature band. With the help of insulated shippers and various gel packs and configurations of gel packs, a package can be designed to hold the needed tight parameters for a given period of time when shipped. We already talked about the hazmat on the previous slide, so let's look at stacking strength, which is another element that a protective package can protect against. Factors such as humidity, stacking patterns, dynamic forces, and time can degrade a box's stacking strength. A package has to be designed with enough safety factors to account for these. Also, depending on what's being packaged, the product can play a key role in offering optimal stack strength performance and it may be able to take some of the load from the packaging itself, so you don't have to use, you can use less packaging material with the help of the product. For example, if you're shipping glass bottles in a corrugated box, if the package is designed correctly and starts deflecting, the glass bottles can help take some of that top load. Other protective elements can include protection against atmospheric changes, protection against oxygen and other gases, and so on.
It's interesting, in our laboratory we're able to see a lot of the types of things that people are concerned about with the package design, and therefore what kind of testing should be done. Paul mentioned that the vibration hazard of the distribution environment is 100% certain, and that's true because it comes from the vehicles on which the product travels. So unless your client, your customer, is next door, it's going to get shipped, and in today's global economy, it's liable to get shipped half a world away. So vibration is omnipresent. The insidious thing about vibration is it's kind of a silent killer. As Paul mentioned, if you have a certain kind of product, typically heavier ones, and heavier ones are closely coupled, if you will, to the vibration vehicle, which means they're stuck there because they weigh a lot. So gravity keeps them on there, and therefore they get the direct input more so of the vibration of the vehicle. Also, larger products can be very vibration sensitive, and our testing has shown that lots of times structural resonance, and that's basically the thing that will kill a larger product, occur at about the same frequencies where the truck input is the highest. So you got a kind of a double whammy. In addition, unless you design that interface, we call it a cushion, correctly, as Paul mentioned, the box can actually destroy the product, which is kind of insidious, but it actually does happen. In the first 10 years of Westpak's history, approximately, much of what we did was simply solve vibration problems with larger package systems. And you can imagine shipping a large and expensive crate to a client. Everyone's got big smiles on their face. The crate arrives in good shape. They open it up, and voila, you have a Heath kit inside, which is basically an old-time way of saying a bunch of pieces and parts, because the crate literally shook the product apart. So these are some of the hazards that we like to point out. And since we don't ride on trucks, we're not that familiar with it's not as intimate a hazard as impacts, because we see impacts, and that's a human phenomenon. People throw things, and that's what happens to a package. But we don't experience vibration levels on a truck. We experience them in a car, but whenever they get severe, we always slow down or fix the problem or something like that. Package can't do that. It's got to survive it, and that's the function of the cushion system. Okay, Paul?
Absolutely. So how do we know what some of these hazards are and why, and what are their severity, intensity, and durations? Initially, ride and bump recorders were used to gather some of this data. They were mounted to a bed of a truck or a rail car, and a pen recorded the levels on a rolled piece of graph paper. The paper was then evaluated manually, and shock and vibration levels were extrapolated from that. These instruments were clunky, as you can imagine, very labor, time-consuming in regards to data collection and analysis. Some of them are shown here, and I think Herb's going to talk about them a little bit. I think he's used them in the past. These instruments have come a long way since then. Newer environmental data recorders not only measure the vibration and shock input, they actually do the calculations as well in terms of vibration power spectral density, calculating drop height, and can even measure temperature, humidity, and pressure. Some of them are also GPS enabled, so you can exactly see when a specific event happens to your package or your box when you ship it. So if there's a bump in the road or falls off a truck or whatever, you can see it on Google Maps. They're pretty neat. Herb?
Yeah, Paul mentioned, Herb's used some of these. Yes, guilty as charged. I grew up with a lot of these. The top item sitting on the corner is a 3-axis. They called it a shock and vibration recorder. It really didn't. It was 3 mechanical little arms that, when they got excited in their various axes, would scribe a little arc on a piece of graph paper, rolled graph paper. It was red paper with white ink over the top, and you kind of scraped a mark and scraped off the white ink. Could you really tell what was going on? Well, sort of. The one right underneath it is a B&K bump recorder, and we actually did use that. I think it's still around here someplace. Had 18 D-cell batteries in it. As you can imagine, stacking those things up inside of something. It was heavy. It actually had an accelerometer, and it would record in 3 axes. And it would give you both acceleration and velocity change, and if you did your homework exactly right, you might be able to convert that information to drop height. It couldn't record vibration, but occasionally it could give you an idea of the drop height. And then the bottom unit is the single-axis one that was often used on rail cars to measure impact velocity of these cars, and it was referred to as a humpilator because it was the hump or the hill that the cars went over in order to get enough speed to couple to the rest of the train. So these are where we come from. That's what we're trying to say here. We've come a long way, baby. But these are the devices that we used originally to quantify much of the distribution environment, certainly the shock and vibration proportions of it. And so all the data in FPL22 and other sources came from these kind of devices. What is absolutely blows me away is that the more recent data, which we're going to be talking about next, or more accurate data systems, they correlated fairly well. I was amazed at how well they correlated. I'll give you an example. A 2-year study of FedEx using the bump recorder gave me an average drop height for a certain package system of, I don't know what it was, 23.5 inches, something like that. Had I gone to the FPL data, it would have given me a drop height estimate of 24 inches for the same weight package. So I was very impressed that I guess given enough inaccurate data, you might be able to come up with something that's worthwhile. But there's a much better way to do it, and Paul's going to tell us exactly what that is now. Paul?
Yeah, so the newer, in this picture you can see the newer environmental data recorders. What's depicted here is a picture of a saver made by Lansmont Corporation. These savers are self-contained with built-in accelerometers, sensors, and memory, and can store information up to 90 days on just 2 9-volt batteries instead of the 18 that Herb talked about in the first generation model. So it's pretty impressive. They're very easy to set up, and the data processing is just done through software, and it's much more easier. It just takes a few minutes. They're only a fraction of the size and weight. They weigh maybe the one that I use, it's the blue one picture shown here, weighs only 1 pound. The bigger green one, maybe 1.5 pounds, 2 pounds, and that small one is less than 1 pound. So they're a lot more efficient.
Not only can they be used for recording the environment, but Westpak has also utilized these, and Paul was directly involved in this particular project of actually measuring things like wind-induced vibration on the solar panels. So they do a lot of things for you, and they're really neat devices. And we highly recommend, if anyone has a question about their distribution environment, that they look into this kind of a service. You don't necessarily have to buy the unit. There are companies that can do that for you. Westpak is one of them. But the point we're trying to make is that we can uniquely define the hazards of the distribution environment much more precisely today using these kind of devices than we could way back in the dark ages when I started doing this. Paul?
So once the environment is measured using these data recorders, it's then analyzed and, if applicable, time compressed. Vibration is a great example of time compression. The levels measured during most of the studies that I've been a part of is about 0.05 to about 0.2 GRMS, and that's on a bad day, with the average being about 0.1 GRMS. However, some of these cross-country trips can take 3 days plus to complete. As much as test labs would love to do so, it's just not feasible to run a vibration test that long. Therefore, the calculated levels or intensity is increased in order to decrease the test duration. This is known as time compression. Now, there is a limit as to how far someone can actually time compress a certain profile without actually breaking it down and destroying the product in the process. Let's take lasagna, for example. You can bake a lasagna at 200 degrees for 3 hours, or you can bake it at 200 degrees for 3 hours, or 300 degrees at 2 hours, or even maybe 350 degrees for an hour. But you certainly can't bake it at 1,000 degrees F for 5 minutes without just burning it. So the same kind of ideology applies here when we're time compressing vibration that's recorded. One of these time compression formulas used by the industry is shown on this slide. Typically, you wouldn't want to accelerate anything more than 3 times what you actually measure.
As far as the time compression is concerned, we were asked during our morning webinar session, when you do this kind of stuff, do you rigidly attach the product to the vibration table, or do you let it bounce? And that's an excellent question. And I answered that by saying, if you're doing a simulation of the environment, then you do exactly what the package is in the environment, namely free floating. So even though the amplitude is increased in order to decrease the time, that's time compression that Paul mentioned, the procedure requires that you let it float on the table. I don't necessarily agree with that, but it's a consensus standard. Most people think that was the right thing to do. If you're doing what we'll call a package performance test, and we'll define that very rigorously in a minute or two, then you should probably rigidly attach it because you're looking for an actual vibration response, and unless a spring mass system, a packaged product in this case, is rigidly attached to the table of a vibration machine, it will in fact bounce because the time compression artificially increases the amplitude, and especially if you're using a random vibration signal, most people do, you're going to have in excess of 1 G a fair amount of time. As soon as that happens, things bounce. So you have this differential between input and response. So that may be a little more confusing than what the topic demands, but it was a good question this morning, and I thought I'd let everyone know about that. Paul, back to you.
Yeah, thanks, Herb. So once all this data is gathered, analyzed, and compensated for, it's then put into what's called a test standard. Many of these you're familiar with. They include ASTM D4169, which is a standard dating back to the initial environmental data gathered. This is a very common test standard and has long-standing roots in history in correlating successful laboratory tests to successful product delivery. A newer standard is ASTM. Sorry, okay, we had an issue with our slides. So a newer standard is ASTM D7386, which is based on more recent data, dating back maybe 10 years, a little more or so, gathered with the help of EPS. This standard includes more recent data, profiles, drop heights, and so forth collected, and seems to serve its purpose well also. Both these ASTM standards are recognized by FDA, because ASTM is a consensus body. If you're a medical or life sciences company, it's recommended that you use one of these standards so you're not questioned by the FDA in case of an audit. Another standards organization that you're most likely familiar with is ISTA. ISTA is very active in constantly evaluating the distribution environment. Their standards are on par with ASTM, but unfortunately they haven't received FDA recognition yet, even though they are in the process and they're trying. Both ASTM and ISTA are recognized by ISO 11607. Other less common standards that we test to include Telcordia for the telecommunications industry, MIL standard for anything military, and IEC, which are European standards.
Paul, we have a question on the standards.
Okay.
How should you decide between ISTA and ASTM package integrity testing? What are the general differences between the two? I think you covered kind of the general differences, but if you could go over maybe how you would decide between ASTM and ISTA.
That's a great question. There's no simple, easy answers. Like you don't say, okay, do an ISTA 2A or ISTA test if you have this product, and do an ASTM test if you have this other product. They're two different organizations essentially doing the same thing. They both consist of tests that we're going to talk about in a minute, which is a series of drop, compression, vibration. And for example, ISTA 3A and ASTM D7386, they're based on the same essential study done by the UPS. They started co-developing the standard together, and then towards the end they went their separate ways. But if you look at the two standards, they're very similar. So it's just a matter of what your preference is. ISTA, you can get certification. So ISTA will actually give you a certificate saying that your package is passed and it's certified. But on the contrary, ASTM doesn't give you any certification. But since it is recognized by the FDA obviously wants you to test to that, and we've had medical customers that have had ISTA tests conducted, and then FDA they were questioned by the FDA, and then they had to go through a whole gap analysis, and it just created more headaches. So it's more which industry you're in, but either one really does the job.
This is Herb, and I'll stick my foot in the door here and say that not only are they very similar, but in some cases they were written by the same people. As you can imagine, those kind of folks who are interested in test standards, and most of them are very knowledgeable people, very dedicated. Sometimes they'll be on an ASTM. That stands for American Society for Testing and Materials, and they'll stay there for a while. And for whatever reason, Lord knows what that is, they might change or quit there, and sure enough, they show up on an ISTA technical committee. ISTA is International Safe Transit Association. So a lot of people who are interested in this kind of thing, bless their hearts, I'm not particularly interested in it, but they are, and we need folks like that. But they wind up being sometimes the same people. That's just another view to say there's not a whole lot of difference between them from our perspective. If you ask those folks, obviously they'll have tons of reasons why they're better than the other guys. But from what we see, it's kind of the old Coke and Pepsi thing. Okay.
Yeah, thanks, sir. And here at Westpak, we have, I'm on the ISTA Council, and we have people here that work here that are on the ASTM committee as well. So we're on top of both standards. So we don't really necessarily differentiate between one or the other. So now that we've had some insight as to what the purpose of a package is and how data is gathered and touched upon the standards, let's look at some of the test inputs common in laboratory testing. These test inputs are common across most, if not all, test standards, as I just said. The first is what we refer to as climatic conditioning. You can see the environmental chambers pictured here. This is also known as extreme conditioning, atmospheric conditioning, or just plain conditioning. It involves subjecting the packaged product to temperature and humidity extremes that may be encountered during shipment. The typical extremes are for winter in the neighborhood of -30 degrees C, for desert 60 degrees Celsius with low relative humidity, and tropical, which is often the most damaging to a corrugated box due to moisture. It's 40 degrees C with high humidity in the neighborhood of 90%. Typical test durations are anywhere from 24 hours to 72 hours per extreme. These tests are usually conducted prior to the transportation tests that we're going to talk about next. Drop test is another element seen across all these test standards. Drop testing is essentially a free-fall impact test where the package or packages are dropped onto various orientations from a specific drop height. These impacts simulate boxes being dropped, kicked, diverted mechanically, assorting sites, and so forth, as we talked about earlier. The drops are either done in one sequence within a standard, such as ISTA 2A, or they're split at different points throughout the test standards, such as with ASTM D4169, D7386, or ISTA 3A.
I'd like to interject that there's other ways to do drop testing, and those of you with a shock test machine can also do a drop test on a shock machine. ASTM, what is it, 53, yeah, it could be 4168. I'm not sure exactly the standards because memory is the second thing that goes. But the point is that you're trying to excite the product package system, and generally drop tests, you just use gravity and try to get the drop as flat as you possibly can for a flat drop and so on. But on occasion, we'll actually use a shock test machine to do drop testing if it's required or we need a very precise type of orientations.
As we spoke, vibration is guaranteed to occur when a package is shipped, and that's what we're going to talk about next. It's a critical element in any test standard. Pretty much all new standards use random vibration exclusively over fixed displacement or sinusoidal vibration. The machines shown here, they can be programmed to simulate vibration resulting from various modes of transportation, truck, air, rail. And if you were doing a saver or environmental study, such as the ones using the savers we talked about, you can directly input those, what you measure, into these tables, and they would reproduce that spectrum. The vibration is typically split between the three mutually perpendicular axes and usually consists of 2 to 3 hours total during a test.
As a testing laboratory, we're often asked to compare various types of inputs, primarily in the area of vibration, by the way, because there's a very noticeable difference between something like a rotary bounce test, ASTM D999, and a true random vibration test, which has its origins in data collected from vehicles. So, we're often asked, how can those two be equivalent? And my answer is, they ain't. They just can't be. However, again, consensus standards are put together by committees consisting of a bunch of different people. In this particular case, on occasion, the committee will say, well, because of this standard's long history, grandfathered in, if you will, and a relatively good history of being able to predict performance. In other words, if it passes this particular bounce test duration and orientations, then the chances are pretty good, or the history has shown that it works. So it's hard to argue with that as well. So a lot of times, you can say, well, from a technical standpoint, yeah, there's a huge difference between these various procedures. Sinusoidal resonance search and well testing, for example, is a total, I'm going to use the word stimulation rather than a simulation of the environment. The environment is not sinusoidal. The only place that sine vibration occurs is in the laboratory. However, it winds up being a pretty darn good diagnostic tool. So if your test protocol is looking or requires a diagnostic tool, there's nothing wrong with sine. You can do the same thing with random too with modern controllers. My point is that you really have to look at the end result that you're looking for in order to pick the right procedures. I remember telling someone a long time ago that I'd never be associated with a laboratory that had a bounce test in it because it's such an antiquated test, and it's nothing more than a grown-up paint shaker, for crying out loud. However, Westpak has, I don't know, half a dozen of these things now, and the reason is because there is a need for them. So it all depends on the end use of the data that you're trying to generate, and sometimes these test procedures do in fact work for us. So that's why there's a wide variety. Paul?
So let's look at compression testing, or stacking, which is another key element in the package integrity test. Each standard has a formula where you plug in either the dimensions or weight, or both, of the package system, and a specific top load is provided. These formula add safety factors to the required top load to account for all the variables affecting stacking strength. Shown here is a compression test system used for static compression tests that are seen in ISTA 2A or ASTM D4169. Now, the ASTM D7386 or ISTA 3A incorporated what's referred to as a dynamic compression test, meaning a box is loaded with a top load and then placed on a vibration table and then subjected to a combined vibration/compression test. This simulates packages being stacked and shipped, and at the same time simulating a box at the bottom of a stack in a pallet or stuck at the bottom of a loaded UPS, FedEx truck and trailer. Finally, let's not forget about altitude. Packages that are non-breathable can often be altitude sensitive. As you go higher in altitude, the air inside a closed system expands, pushing against the package walls. This is why a closed bag of chips or a bottle of water expands when we travel up in altitude, up a mountain. It's conceivable that a bag or bottle can burst or lose internal pressure as a result of this. I've seen corrugated boxes burst open due to multiple bags expanding within. In this test, we typically take the packages up to 14,000 feet, close to the limit where someone can breathe without the assistance of oxygen, to see how they're affected. Mountain roads are usually worst case in aircraft shipment, as most planes are pressurized to 8,000 feet.
There were a number of questions that occurred about the whole area of altitude testing. We say that most aircraft are pressurized to 8,000 feet, and that's true. In fact, almost all of them. And the reason is they're all piloted by pilots, and the pilots demand 8,000 foot because they go up and down in these aircraft, and that pressurization differential will cause nitrogen asphyxiation in the blood, what we call the bends, if they're overexposed. So this is that was one of the reasons why 8,000 feet is the normal pressurization level. Now, there are some variations to that. Some of the newer aircraft, I think the Boeing 787 Dreamliner, they call it, is pressurized to 4,000 feet because it keeps more moisture in the atmosphere, and it's not quite, doesn't dry out near as much. Those of you who have flown in that plane know that there is a difference. Another question was, okay, so if 8,000 feet is the limit that you're expected to get exposed to, how come you test at 14,000 feet? Isn't that an overtest? And the answer is no. Strangely enough, you actually have higher altitude exposure on a truck than you do on an aircraft. As trucks will go over the mountains, and there are mountain passes in the neighborhood of 10 to 11,000 feet. So you can actually have higher exposure on that. There actually was a war story about 20 years ago of a truck filled with snack foods, and it actually floor loaded, so it was real tight in there, and it was going up the front range of the Rocky Mountains, and all these little bags are then expanding a little bit. And boy, I'll tell you, they just expanded to the point where there wasn't any more room in that truck, and it actually blew the walls out. And since the walls support the floor dropped away. They had like less than 5,000 pounds of load on it, and it destroyed the truck. So there are obviously some war stories about it, but anytime you have a closed vessel, either in the product or the package, for example, a foam material, a closed cell foam material, is going to expand in response to reduced atmospheric pressure that occurs at higher altitude. So don't ignore these subtle little things. For example, a lot of folks ship products in a kind of a bubble wrap or a bubble film material or a kind of a bubble bag, loose fill. Be a good idea to check that against altitude levels of 14,000 feet before you really get into doing that a lot, because you can be surprised. Paul, back to you.
Thank you, Herb. So the point of this, the topic is package integrity testing, but it's not to be confused with package performance testing. These are two different types of tests that are done in a laboratory. Package performance testing is often quantitative and is used to evaluate a specific functions of a package. This can be evaluation of the ability of the cushion system to mitigate shock, done by mounting accelerometers and doing a drop test to evaluate cushion performance. It can also be done to determine resonant frequency of the package system and compare it with the natural frequency of the bare product. Package performance testing is often used to optimize a package design and takes an in-depth look at the actual numbers. Package integrity tests, on the other hand, which is the focus of discussion here, is strictly a qualitative test to see if the product will get to its destination in one piece. It is usually a pass-fail test in association with the test standard it's tested against. It is required by regulatory. It's used to validate a package system, and typically larger sample sizes are used to increase confidence.
This is a really important point that Paul brought up, and I'd like to emphasize it, namely that the performance test, and by the way, these names, package performance versus package integrity, are merely ones that we've applied because it's not universally applied in the industry. I'll give you a good example. ASTM D4169 is a really good package integrity test, in our opinion, and per our definition. However, if you look at it, the title of it is package performance testing. Okay, so it's not universally applied, but we decided to do it this way because of the difference between these two types of tests and the fact that many people confuse them, and we don't think that's a good thing. Again, a performance test is quantitative. In other words, numbers. You got to have numbers for a package performance test. One of the reasons for that, obviously, is to determine pass or fail criteria. But if you know that you pass by a wide margin, and you know that if you have the numbers, then you don't really need a large sample size. For example, if the fragility of your product is 80 Gs and the package transmits no more than 40 Gs, you've got 100% headspace. So you know that going in. But you only know it if you do a performance test where you're actually getting quantitative data. In other words, you get the numbers out of the whole thing. Another important thing that this kind of a test does for you is to give you a determination of headspace, or what people might call margin. Or had the boss ask you, okay, so it's a good package design, huh? How much margin do I have? Break. Well, if you did a performance test, you would know. Hey, boss, I got 100%. You'd also know if you're overpackaged. And if you got 100% margin, you're probably overpackaged. So you can do a lot of this kind of analysis once you do a performance test. You do have to know, however, the limits that the product can take, because the product and package work together as a system. Okay. Now, this is opposed to an integrity test. An integrity test is envision some big scooper hands that go out and they scoop up this distribution environment that Paul talked about earlier. They bring it into the laboratory, jack up the level in order to reduce the time, and subject the package system to that product package system. And then the end result is you simply open it up and make sure the product is in good shape. Good shape. What does that mean? Well, generally speaking, we like to call that the kind of condition in which you would want the customer to see the product. And that's often used when it's more difficult to determine product fragility or product sensitivity in terms of shock or vibration, etc. However, as Paul mentioned, it does require a larger sample size in order to be statistically significant. And since you don't have any margin analysis available, you have to have a sample size big enough in order to actually make a judgment about its validity, statistically speaking. And Paul's going to talk about that next. So, Paul, take it away.
Yeah, so speaking of sample size, first of all, we want to stress that the sample size is not specified in any test standard. I get this question all the time. It's determined using two different various types of analysis. When doing package integrity testing, attribute statistics are usually applied, mostly by the medical industry, where most testing is pass-fail and sterility is a key attribute. For attribute statistics, especially for first-time submissions to the FDA, a 95-95 rule is typically applied, meaning you have 95% confidence that 95% of your data is reliable. In absence of any other data, this is a safe play and a safe sample size to choose. This results in a sample size of 59, so it's easy to remember. 95-95, you switch the numbers, equals 59. However, we do have customers and clients who use a 90-90 or even an 80-80 rule. Just as the reference sample size for a 90% confidence, 90% reliability is 22. Variable sampling is more often used for package performance testing that Herb just talked about, where a specific point of interest is measured. With variable statistics, there's no easy rule. You can pretty much use any sample size that will provide you with the data you need. So what are some advantages and benefits of doing a package integrity test? If you're shipping your package back and forth, for example, from the East Coast to the West Coast as a shipping study rather than doing a test in the lab to assess its performance, your sample size is 1. And in statistics, a sample size of 1 is considered insignificant. The testing we do in the lab is based on many rounds of shipping studies and data and is more representative of the actual transportation conditions than just as one single or even 2 shipments. Another significant advantage of lab testing is the speed in which the tests can be conducted compared to field studies. Where a field study may take weeks or months to complete, a package performance test in the lab will only take you about 1, maybe 2, a week at the most. In addition, lab testing is very repeatable. This is highly desirable and should not be overlooked. The repeatability of the test inputs will allow the engineering team to evaluate trade-offs in the product package design, including different materials, suppliers, processes, and a variety of other variables, including whether or not to proceed with the project in the first place. This is perhaps the best reason for using a lab testing technique over the shipping test. Sorry.
I'd like to
it seems like we're having a problem with Herb's mic here, so bear with us just a second. Paul, do you have any other comments about the advantages and benefits?
No, it's just, when you do a test, the most important part is the repeatability. That means if you have, you're testing different product across the line, when you have product A versus product B, you can compare them to each other. If you're doing a just one shipment across, the country, one box could go through one distribution cycle, and another one can take a completely different route, so it's not repeatable. I think we got Herb back on, so.
I didn't know Herb was off, but I guess I'm back on now. Anyhow, I remember doing testing, ship testing, and being very happy when I got the results back, and shipping out, in some cases, a very expensive product, and then having damage in shipping. I couldn't figure out what in the world was going on. I did everything according to the rules. The formula for statistical significance has n-1 in the denominator. Well, if you have one sample, that means n equals 1. 1 minus 1 is 0. You have 0 significance, and that was brought home to me big time. So if you do ship testing in order to validate a package system, make sure that you do more than one, and the sample size of many is considered desirable. But that, as Paul mentioned, that's one of the reasons why a laboratory test winds up being pretty significant. You know exactly the level of the inputs, and by the way, those levels are generally, we try to shoot for 3 sigma. So, in that regard, but the whole point of the matter is that once a test in a laboratory is done, you have very high significance in the data and very repeatable for whatever changes you want to make, suppliers, materials, designs, whatever. Paul, back to you.
Okay, thank you. So how do we quantify success? How do you know, what's the acceptance criteria? Well, this is pretty straightforward. You first determine what's considered acceptable and what isn't. I'm assuming that product functionality is a must. I mean, I guess I'm hoping it is anyway. But what about the cosmetic wear or excessive package denting? How about label legibility? That's a good one, because do you want your label to be completely free of blemishes? Do you want it to just be perfect when it gets to its end user? Or do you just want it legible as long as people can read it and you don't care about smearing? So I know that the medical industry is pretty keen on that one. So once this criteria is set, you would then evaluate based on these and make a decision from there, whether you need to redesign and retest or whether it's to pass and you move right along. So with that, pretty much wraps up our webinar. Thank you all for listening. If there's any questions, feel free to contact us here or just ask Greg right now. I think we have a few minutes to answer some questions or field some questions.
I'm not sure that my microphone issues have been resolved, but I can hear me, so maybe they are. I do want to emphasize that Westpak takes seriously this whole area of you know, terminology and where things come from and all that kind of stuff. In addition to what we believe our goal or duty or whatever to be to inform our relevant public, you folks, of exactly what we do and how we do it and where it came from and all that kind of stuff. And we do plan to continue this process and get in-depth into a number of these different areas. And we have that schedule arranged for next year, and we'll probably be releasing that shortly. So if there are specific areas of protective package design or testing or pharmaceuticals you will be carrying that forward.
We have a few questions here. How should you decide among testing a single case, several cases, i.e., or a pallet load of product? How do you decide between that?
So that's a great question. It all depends on how you ship the product. So does the pallet get broken down anywhere into the distribution life cycle? Do you take it to the distributor and the distributor breaks it down and ships it from there? We know that the smallest package or the smallest, I guess, level of your package is the worst case. So if you've got a stack of boxes, 100 boxes on a pallet, the pallet actually acts as a secondary package and adds a level of protection typically. You might argue that against compression, but even with compression, we know that the smallest shipping unit is often the worst case. So if it's going to get broken down into pieces at any time in distribution cycle, then just test the single boxes. If those pass, you probably don't have anything to worry about when shipped on a pallet. But if it's only on a pallet and it's only shipped as a unitized load, then we should test just the pallet, just because you don't want to over-test it if it's never going to get broken down.
I should add that outfits like Procter & Gamble, for example, who do both, will test both. They test both full pallet load configuration and individual shipping configuration called LTL, if you will, because their systems will most of the time be shipped both ways. So, Paul, that was actually correct.
Great. The next question is, can you guys speak on the time compression formula and how monitored field data applies back to that for ASTM and ISTA? Do they actually publish the formula that they use for their time compression?
Do they publish it? They do time compress it. As far as what formula they use, I can try to ask them and get back, but I do not know the answer to that right now. Herb, do you?
I do know that when you record the data off of a vehicle, I guess you will get a type of acceleration versus time signature, and it's a bunch of squiggly lines that go on forever. and the ability then to take that information and put it into a spectrum is a matter of individual setup, if you will, algorithms used on that data. To the best of my knowledge, those are not published, but if you're interested, I know that the manufacturers probably would not mind sharing that with you. I mean, they have no reason not to. However, once it's put into a spectrum, then for example, ASTM, the D10, the D1021 infringement, or I forget which one does it, will actually determine assurance levels for their data, and they have done this based on the amplitude and the time, to a lesser extent, that a package system is exposed to that. So it's both the recording of the data and the use of the data, or this amplitude, time, compression numbers or factors that are applied. But it happens both in the recording of the data and in the use of the data, and those are two separate functions. Greg?
Cool. Thank you, guys. Another question. ISTA represents 2A as a standard to use for international shipment, 3A for small parcel shipment. If both modes are in your supply chain, should you do both tests?
So I can answer this one. Actually, so it used to be in days past that ISTA just had the 4 or 5 standards, and the 1A, the 1 series was used to call the domestic, and the 2 series was the international. They no longer call it that. Right now, currently they call the 2 series a partial simulation, meaning it's not a full simulation and it's not based on the more recent data. However, the 3 series now they call the general simulation. So it's not just small parcel. The 3A is for small parcel. The 3B is for large packages and large crates. The 3E is for unitized loads and so forth. So their 3 series tests are the general simulation, and all the 2 series tests are the partial simulation. They no longer differentiate between international and domestic, because we find that through some recent studies, when they travel internationally, either by vessel or by air, the vibration in the test inputs aren't that bad as previously thought. The worst case for any package, even temperature, humidity, vibration, shock, is the truck route.
Okay, great. The last question we have here, do you have recommendations? Do you have recommendations for quantitative package integrity testing approach, ignoring inherent variables in various materials? So is there, Herb, it looks like you want to field this one.
Let's see. Quantitative and integrity. Well, those are 2 different things. If you're doing integrity, you have quantitative.
It looks like you're cutting out, Herb, so if you could borrow Paul's mic there to finish up.
Sure, I heard that. Okay. Quantitative data is associated with the performance test, and integrity is a simulation. Okay, so we got to get those 2 squared away. When you're doing a quantitative test, then there are procedures for the whole thing, and yes, it does work. I'm not sure that answered the question. Maybe you could repeat that for me, Greg.
How should one decide between, or no, where is it here? Sorry, I got scrolling here.
That's pretty cool when you can screw up the moderator, kind of.
Where is it here? Do you have recommendations for quantitative package integrity testing approach, ignoring the inherent variables in various materials?
Well, yes, we teach that. That's the subject of the packaging dynamics classes at the various schools, Michigan State, San Jose State, Clemson. I don't want to leave any out here, but those kind of folks, they normally teach packaging dynamics. I did that for quite a while at San Jose State. And yes, there's very definite techniques. In fact, I'm glad this question was asked, because next year, calendar year 2015, we're going to be teaching a series of 6 webinars on exactly that topic. How in the world do you go about doing it? Some people call this a 5-step method, some 6-step, other people call it crazy, but we're going to be teaching that whole thing, and that's going to be starting next year.
Cool. Thanks, everybody, for your questions. If we didn't get to it, we will follow up with you guys after the webinar, so thanks for sending them in. We really appreciate the input during the webinar. I think it makes them better. Herb and Paul, thank you for your time and effort in putting this on. If you missed anything or would like to listen to the webinar again, please check the Westpak website at www.westpak.com under the Events tab. The webinar should be up there shortly. All people registered will receive an email within 5 days with a copy of the recording and a link to download the slides. Please join us in San Jose for our open house on October 2nd. You can check our website for registration details. Also, check our website for upcoming events and our next webinar. If you have any other questions that you think of after the webinar, please email them to projects@westpak.com. If there are any other webinars you would like to see us offer, please also submit them to projects@westpak.com. We will be sending out a survey following the webinar. Please fill out our survey, as we're always looking to improve the process. Thank you all for attending. I'm Greg Schwinghammer. Make it a great day.